Alright, hello and welcome. Today is April 1st, April Fool's Day. And the fools are all of us, I guess. Because we are here still learning. We'll see, we'll see. One day, everyone else will be the fools. Because we're the ones who carried on. Alright, so today we'll talk about inductors. Mr. Z, school is RIP. What? What does that mean? School is school. School is where we are. School is not a location. Remember in like, what was it? Infinity Wars, was it? Or Ragnarok? I can't remember. Where it's like, where is Valhalla? Valhalla, was it, was it the ship, or was it you know the new location? No, Valhalla is in all of us. Lol, I get a battery ad. How fitting. Perfect. Oh, sorry, it's not Valhalla, it's Asgard. Very good, very good. Valhalla would be the uh, actual thing that they modeled Asgard over, right? I guess Valhalla would be the Norse heaven. It's not? What do you mean? Oh, actually, they can go to. Oh, yeah, you're right. You're right. Asgard is just their home. After their death, they can go to Valhalla still, even in the Marvel universe. I suppose there's like a heaven thing. Yeah, Jacob's right. Jacob's right. There we go. We got our Marvel Cinematics universe stuff all squared. So we back in the mine. All right. So anyway, let's go and continue. Inductors. Um, as we saw yesterday, we were using them basically to do cool things inside circuits. So today we're going to slowly combine the properties of magnetism and apply them to circuits. That's the name of a game on Steam. Side to side. What? Side to side. Oh. All right. Anyway, so here's an inductor. It's basically your solenoid, but a miniaturized version that you can fit inside your circuit. Now, there are big solenoids also, and when we have plenty, if you ever come back to school, you can come by and look at all the stuff that you didn't get to play with this year. All right, let's say it has a certain length, and from here on out, now that we're finally going back into the circuits unit, but with magnetism, we're going to stop using the capital L. We took enough L's for one lifetime. Uh, we'll use curly L to represent the entire length, right? Because L is actually a variable, not just length, not the geometric variable, but an actual physical variable. I feel like I'm losing my voice. I think I probably sound different today. Well, anyway, let's say current is running through, and it's going, and it goes around, and then it'll come back down the other way. And so this is basically a small solenoid, right? What's the magnetic field inside? What does B equal to? Chat, what does B equal to? I need to drink some water. Yeah, everyone gets old. Mu naught n I over I. N I over L. Good morning. So let's go and write it in this format. So it would be mu naught, permeability of free space, times the number of loops, n, times I, divided by the total length. In this case, it's curly L. Okay. All right. Now, based on measurement that you can make after putting this inside a circuit, you'll see that the total flux is proportional to the current that you use in your circuit, I, times some number, and yeah, and this number happens to be the constant of proportionality that makes the two sides equal. Constant of proportionality, and we can call this the inductance. Or self-inductance, really. Okay. We know that flux normally should be the total amount of magnetic field that goes through a given area. If you have multiple loops, then it's n times that. So NAB, N-A-B. And it is a dot product, so let's go and do dot product. So cosine of theta, like so. Recall that if I had a single loop, of radius r, of course our dA vector would be that away. And let's assume that our magnetic field is also in the same direction, like so. So we get 100% flux. Therefore, your theta, the angle between your area and your magnetic field, is just 0. And this means that cosine of theta gives you 1. So you get 100%. Okay, so setting the two magnetic flux equations, Henry, yeah, that is the unit, very good. Do you guys remember what the unit is for flux? Magnetic flux, I should say. Units for magnetic flux. While I set the two equations equal to each other. Weber's, WB. All right, Ryan Davis. Now, of course, this will goes to 1. So let's just say that L times I is equal to NAB. L times I is equal to, well, N times area. The area is just pi r squared. Yeah, pi r squared. And the magnetic field, is the magnetic field inside a solenoid. So that would be mu naught, well, what do we have? Mu naught n times I divided by curly L being the length of the solenoid. Alright, let's go and simplify and solve for L. I get mu naught times n squared times pi r squared over L. Okay, and this is your self-inductance inside the inductor, and of course the units is capital H on the Henry, Henri in French. All right, so ultimately all it is a constant of proportionality that relates the flux and the current in your system. Okay. All right, so let's go ahead and put this in a circuit and see how that affects it. So let's do a simple circuit with a battery, sorry, EMF, like so. Or just call it V if you want. Here's a resistor, and then we will draw a nice inductor. And let's go and put a switch right here at the start. Like so. All right, so we know that we have a current flowing out of the positive end here. And so let's do a current flow diagram. Well, as soon as I close the switch, of course, so current will flow through around in a clockwise fashion here. Let's go and define a new term called the steady state. Steady state. Okay, the steady state is where the inductor acts as a wire. Okay, so no resistance, ideal wire. All right. Now, the first thing we want to do is let's go and put in our polarities and define the direction of our electric field. Actually, I should have just called it V. Let's call it V, because I'm about to write E, and I don't want the E to look like my epsilon. So I'm going to change the epsilon to a V. Okay. We can say that the electric field points to the left here, this way, from the positive towards the negative, right? From the plus charge to the negative charge, that's the direction of the electric field. What epsilon? Oh, okay, never mind. Epsilon was the EMF. Okay. And in an ideal case, it turns out that E should equal 0 here for our inductor. And we'll say that the electric field here is to the left also, E. Like so. Because now if you look at it from the resistor's perspective, right, all the charges are flowing towards the left side here, and so that'll be the direction of the electric field. Okay. So this is E from the perspective of the resistor. Here's E from the perspective of just the battery. Just the battery isolated on its own. Okay. Now the inductor, because it's looped around like this, will produce a magnetic field, and that magnetic field will apply a force on all these charges. Okay. It will apply force, which means that the charges will move, which means a current will be induced the moment that there is a change. So whenever we activate the switch on or off, we have to do it at that point because our battery is a DC battery and it's a constant voltage supply. Therefore, when it's actually on, and sometime after you close the switch, it'll supply a constant current. And if it's a constant current, then there's no change, and if there's no change, then there's no induction happening. But the moment you actually turn it on, there's a change, and that change will induce a current. That current will fight the change, the original change that you are causing, which means that the inductor is able to act like a battery. And I'll draw the battery, this hypothetical battery, in the opposite direction because it's going to fight it. So inductor it acts like a battery in that it'll fight the current. It pushes the current the other way. Yep. Okay, because when you turn it on, you're trying to push current to the right, but the inductor will do the opposite and try to push the current back to the left because it's going to fight the change. Oh, it's an anarchist. No, it's actually that's not an anarchist. It's more like a conservative of some kind. Someone who loves status quo. A buffer solution. Well, that's what the inductor does, but because it does that, you can do various things, right? It only does that when there's a change. It doesn't always do that, number one. And number two, when you have these changes, you can wirelessly affect other inductors and essentially transfer power over from one side to the other, kind of like what we saw yesterday. Okay. All right. Moving on. Let's go ahead and write some equations now. What is the induced voltage? Well, the induced voltage Vind for here is equal to negative. I'm going to say negative because it's backwards. Negative d phi b dt. Okay, and therefore we can say that based on what we wrote down earlier, that the magnetic flux is proportional to the current itself. But if we want the change, then it's going to be the change of Li. Let's keep the negative sign. L is a constant, right? So L is not going to change. So if the flux is changing, the only thing that can change is the current. So di dt. Okay, so this is basically Faraday's law, but we're applying it to our inductor now. Okay, so let's go in now, knowing this, we'll go ahead and do a Kirchhoff's loop rule. So let's do a Kirchhoff's loop rule, starting with our battery, and we'll go around this circle here, starting with our battery V. So let's do a loop rule. Okay, start with V, and then we have V minus L di dt minus IR, IR being whatever current we have in our system, times the resistance of this resistor. And that's the end of the loop, so it equals 0. Yeah. Now, the other equation we have is from Maxwell's equation number 4, where closed loop integral of E dot dl must equal the change in flux, and the change in flux is negative L di dt. flux for time at least. All right, so these are the two things that you have in your arsenal. Let's go and use Kirchhoff's loop rule to kind of solve for the current in our system. Using the loop rule, we see that IR minus V is equal to, I'm just moving things around. I should have just moved it the other way. No, let's move it the other way. Let's move the L di dt to the other side so it's nice and positive. So we have V minus IR is equal to L di dt. Like this. Okay. And now, in order to solve this, we need the variables to be on the same side, right? I'll put parentheses here. We can multiply by dt to both sides, and then get rid of this L and move it to the other side as well. So basically we have 1 over L on the left side times dt is equal to 1 over V minus IR times di. Okay, and we need to integrate both sides. So let's go and integrate. We also need bounds. Don't forget your bounds. What are my boundary conditions? Well, we'll start at 0 time. And then we'll go on to t amount of time. Okay? Now, what about my di? Well, at 0 time, what's my current? Let's take a look at the circuit again. Here's the circuit. At 0, the switch was open. We have to close the switch first, and then time starts. So we start with 0 current. Okay. What's the question, Torben? It's V minus inductor minus IR. Yeah, it is. That's the loop rule. And we're going to go up to I amount of current. Okay. I amount of current. All right, now it's just a simple problem, right? L is a constant. We can factor it out. Integral of dt gives us the t. So on the left side we have t. Let's use a different color. T over L. From 0 to t, that's just going to give you t. Okay. Now on the other side, it's slightly harder. Let's leave it alone for a second, because here we have to do a U substitution. So let's do a U substitution. Let's let whatever's in the denominator equal to U. U is equal to V minus IR. Wait, why is the initial current 0? Because the switch is open at 0. Shouldn't time start when the switch closes? Yes, it starts from 0. What? Charge has to flow out, right? So at 0 you have 0, and then as time moves on, at one infinitesimal amount of time later, you have the first few charges flowing out. That's what current is. Now, because it's a change, remember, because it's changing, right? The inductor has 0 current flowing through. it has zero magnetic field. All of a sudden, when you close that switch, now there's an influx of current which is going to produce a magnetic field. There's this change. And since you made that change happen with almost no time, then there's going to be an infinite amount of force pushing you back the other way almost, right? That's how it feels like. So the inductor is able to fight it back, but it's a losing battle. It's infinite if you did it in zero time. Of course, there's no such thing as zero time. All right, U substitution, U equals V minus IR. Let's go into du. What is du? Du is equal to negative. Or V would be a constant. It's the battery, so V goes to zero. The derivative of a constant is zero. And so derivative with respect to I would be negative R di. Du di. So di is equal to negative 1 over R du. If a wire creates a magnetic field and that magnetic field does work on a different object, doesn't that create energy? Well, how did the wire create the magnetic field in the first place? In order to create that magnetic field, charges had to be moving. You had to have current. And in order for that current to happen, charges moved from some sort of high potential to low potential. So you used up electrical potential energy to do that, right? So no free stuff. Got him. Good job, Mystery Wizard. This kid trying to create some free energy. Who does he think he is? Can you go watch Electro Boom? But does that affect the current? What affects the current? Like the work? Well, let me finish this integral. Does the work affect the current? No, the current is going to be based on whatever voltage difference there is between the wire, or like the ends of the wire, let's say. And what you do with it is on the other person. Now, if the magnetic field applies a force onto an object, technically that object, Newton's third law tells you that the object also applies a force onto your original object, right? So Newton's third law still works. All right, let's go and replace the di. And so what do we have? We have just on the right side, on the left side we have T over L. On the right side we have negative 1 over R. Negative 1 over R, integral of 1 over U times du. Now I'm not going to change my bounds because I'm just going to do the integral and then resubstitute so that we can keep our bounds. Yay. We can move stuff around from here. You can see how it's negative R over L times T. Is equal to 1 over U is just the ln of U, and U is V minus R. V minus IR. And we're going from 0 to I. Now don't just ignore the bounds, you actually have to do them. A Doe inductor. That must be the new AP question. I mean, they did Doe resistors, right? Is equal to ln of, if I plug in I get, If I plug in I for I get V minus IR. Okay, and then if I subtract ln's, remember when you subtract ln's, that's the same as the quotient, minus ln of 0. Now, it's not ln of 0, I should say. It's ln of V minus 0 times R. Now, the 0 only affects the IR part. There's still a V there. So, V. Okay, just exponentiate. Boom, boom. There we go. Take care of the ln. So we have e to the negative r over lt. I don't like how I'm writing this. Let's try again. Wow. That's maximum zoom. Darn it. E to the negative r over lt is equal to V minus IR over V. And so we'll do some swapperoonie here. Solve for I. So how can I solve for I? Well, if I divide both things by V, I get 1 minus 1 minus. Well, let's not do the 1 minus. Well, we can. Well, do you want to do 1 minus? Sure, let's do 1 minus. 1 minus R over VI equals e to the negative R over LT. Move things around so you get I by itself. I as a function of time. And then, oh yeah, multiply by the reciprocal, so V over R times 1 minus e to the negative R over LT. All right. Now, what is V over R? What is this thing in the front? V was the voltage of the battery. R is the resistor. So what is V over R? Ooh, so if I go back to our actual circuit, okay, remember in a steady state when there's no change, the inductor actually acts like a wire. So if the inductor acts like a wire, then essentially we just have a battery and a resistor. And if I just have a battery and a resistor, the total current in our system is just the voltage of the battery divided by the resistance of the resistor, V over R. So this would be the maximum current, not our initial current, but maximum current that we get. So it's I max. And you can see how at infinite time, e to the negative infinity approaches 0. So this parentheses thing turns into 1. And so at infinite time, we get maximum current. Imax 3D. At infinite time, we get max current. So V over R is Imax. Okay, and we can also rewrite this R over L thing similar to how we did with capacitors. We can say that the time constant tau is equal to L over R. That's my question, Torben. You're supposed to do it. If you look at these capacitor notes, we're basically following this exact same thing, except we did it with an inductor. So, ISBO, that is the next step. Okay, so since tau is L over R, okay, we have negative T over tau again. Oops. Like so. It goes from 0 to I max. Yep, it goes from 0 to I max. So let's go and do it. Okay, so of course the y-axis is our current in amps. And of course T in seconds. All right, and our total, no, let's go and do a horizontal asymptote and exponential clip. Yeah, so like so. This horizontal asymptote happens at I max. We'll just say V over R. And so we start from 0 and then we curve up. Okay. Now after tau amount of time, to strategically divide this. There we go. After tau amount of time, what happens to our charge? What? Are you sure? If t equals tau, then I have e to the minus 1. What is 1 minus e to the minus 1? Let's use our buddy Wolfram alpha. 1 minus e to the negative 1. 63%. Excellent. I tried my best, but I think it hits it. Oh, it's just over 2/3. No. Let's see. Darn it. No, that's not what I want. This was right. Let's just move. Oh, wow. This is not my day. Let's move it slightly over here. There we go. After tau amount of time, we are at 63%. 0.63. All right. Now, question. Let's do some follow-up. Right. Of course, it would take an infinite amount of time to get to I max. But if I change L, let's use red. Red represents a different circuit where we have a higher L. How will our curve change? Chat, how will the curve change if L increases? Okay. Basically, will it take longer to hit I max? Because I max is I max. I max is just the voltage of the battery divided by the resistance of the resistor. And of course, at infinite time, you'll eventually reach I max. But will it take longer to reach I max, or will it be quicker? Well, if uh, if L is bigger, well, just take a look at the equation. L is in the denominator. So if your denominator is bigger here, what does that mean? Okay. Does more inductance mean it fights harder? Well, based on induced voltage, you can see how the induced voltage is directly proportional to the amount of inductance you have, right? If you have a stronger inductor, you're going to fight it for more than a weaker solenoid, than a weaker inductor. So yeah, it takes longer. Okay, or just look at the time constant. The time constant tells you how long it takes for you to charge it up, 63%, right? So if L is bigger, then it's going to take a longer amount of time to charge up to 63%. Okay? And of course, if I follow this model, then having a lower inductance, or a weaker inductor, having lower inductance would mean that it charges up faster. I shouldn't say charges up. I should say it reaches steady state at a faster rate. Hey, that rhymes. I wish I could do this all the time. Ooh. Good job, Mystery Wizard. All right. Yeah, I think this is good enough for today. Tomorrow we'll look at switching back and forth and seeing how we can do this in charging and discharging states. We'll take a look at the power and the energy and finish it off with the LC circuit. All right. So thanks for tuning in. Should we keep going? Actually, what time is it? It's 12. Yeah, I think that's good enough. Thanks for tuning in. I'll see you next time.